Many appreciations for the opportunity to speak about our work, Twitch's CDN, as an open population ecosystem. We're from NTU, and I'm Polly Huang. After the introduction, two of my colleagues, Xu Cheng and Wei Xiang, they will follow up with more details. Let me start by explaining why we study Twitch. It belongs to one of these major video services on the internet. The first kind, very well known, such as Netflix, YouTube, we watch playback videos. Second, we're using it more and more commonly today, such as Zoom, Google Meet, for the meetings, over distance. So these are called the conversational videos. What we're sending are actually live audio, video, and back and forth. So you can imagine the delay bandwidth requirement in the second category is higher than those in the first category. But the viewership, on the other hand, in conversational video, oftentimes we speak within a small group of people. So this is so. On the other hand, for playback videos, the viewership could be huge. Now, the third kind that is on the rise is called the live video broadcast, and Twitch belongs to this category. Now, YouTube Live, it's also more used these days, because of the content being live still, delay bandwidth high. And the viewership might be a surprise to many of you, is just as high as those in the playback video. And here's an example. Super Bowl, it's one of these major American football events on TV every year. It draws in millions of viewers. For example, in 2018, 98 million viewers tune in to watch, and it's well known the commercial time is the most expensive among all TV programs. But look at this guy here. LOL, it's one of these major online games. League of Legends, the World Championship Final. The scale of the game, the viewership is just as bad. I don't know if it's good or bad. 99.6 million viewers. And you know what? This event is broadcasted only on Twitch. So Twitch as a platform that hosts esports and gamer streams a lot. It actually draws in lots of viewers as well as traffic. We know already, this is not news, more than 80% of the internet traffic is video. And live video is growing really fast. In the pandemic, 2020, just between March and April, the growth rate is 45%. And Twitch is the one dominating live video traffic. In fact, the amount of traffic it's generating is just behind Netflix, Apple, Google, all these internet giants. Twitch's system is in fact straightforward. We have streamer on the left uploading video stream to the internet, and the viewers drawing the videos off of the internet. The subtle part is this. In order to allow upload downloads, we have these servers around. The videos are stored here and there. So we do have a CDN system behind, trying to satisfy the QoS requirement and satisfy the growing viewership. So you see the scale and accessibility of the CDN is a key design factor in a live streaming system as successful as Twitch. But you know what? Until today, little is known about Twitch's CDN. Our motivation is very straightforward. We just want to find out more. And the first bottleneck is to try to monitor Twitch's CDN continuously. You know what? We are not the first one curious about discovering these video services CDN and hopefully repeatedly. There's a string of work already, but many of these efforts are one-time only. Because what we do there is we repeatedly request these videos available on the platform. And by observing the IP addresses of the servers providing the videos, then we discover the video CDN. On the internet today, it's not exactly to do because of the probing overhead and because of where we can set up these probers. Second challenge, which might not be addressable really if you think about it, is it's always hard to argue how good the coverage is the CDN would discover, unless these companies would tell us exactly what the CDN deployment is. And what we're trying to say here is let's focus on the first challenge that is more addressable. And what we see towards long-term monitoring of a video services CDN is a two-phase scanner, two-phase prober. In phase 1, instead of doing exhaustive probe through all videos, we only sample, okay? And as a result, we only generate lightweight probing traffic. In the meantime, we're able to estimate the CDN size. Therefore, when we see the size change is significant, then we can go on and conduct the exhaustive full scan. Now here, CDN size is a very reasonable and intuitive indicator, okay, to trigger the full scan, because if there is a significant increase, indicating demand growth, indicating potential of a misconfiguration. A significant decrease, declining demand, or some sort of maintenance going on, or weird persistent outage going on. Now, in this paper, however, what we're talking about is how we address phase 1. How do we do lightweight sampling and yet estimate the CDN size accurately? To that end, we borrow from ecology the capture, mark, recapture methodology. So ecologists have been using it to estimate the animal population in the wild. If you think about it, comparing animal population versus server population in a CDN, both are costly to survey, and we both, unless we're God, we don't know the ground truth. Okay, so our work is an attempt to try to apply ecological statistics to the problem of estimating server population in CDN. And you see now how we get the title of the paper, Twitch's CDN as an open population ecosystem. And that takes us to our problem statement. Our aim is to do lightweight sampling and yet being able to estimate Twitch's CDN size accurately. And this is necessary towards long-term monitoring in a cost-effective way. Coming up next is the two models we have tried and our effort collecting a data set so that we could understand the trade-off between the traffic overhead versus the CDN size estimation error.
Thus, we use the CIS model. CIS model is designed to estimate an open population, which means the population may change over time. There are two terms in CIS model. First one is survival rate, which means the probability of animal to survive to the next round. And the capture probability is the probability that the animal to be captured. The two terms is both vary over time, and the capture method is to capture, mark, and release the animals continuously. And the calculate method is to use the maximum likelihood estimation to co-estimate the population, survival rate, and capturing probability at every capture. At capture T, we can estimate the population NT by the number of market animals NT over the proportion of market animals P and T. Okay, to get the key term NT, we present the most intuitive derivation in this video. And we can consider the chance of market animal be caught again in the future should be same in the capture T and outside the capture T. Okay, we can take a look at the left side of the equation, the RT over CNT, which is mean the probability of animal in the capture in the round T to be recaptured in the future. And the right side of the equation is ZT over NT minus CNT, which means the animal not captured in the capture T, but it is marked to recapture in the future. Okay, by the equation in the last pages, we can derive the following equation, NT and the equation of the P and T. We can know that the RT and ZT is account for the chance of recapture in the future. So that is why the CIS model population estimation in the past will adjust because to fit the new data. Dealing with the bias for the small sample, we can plus 1 in our equation. Hello everyone, I am Xu Chen. I will talk about CNR model. We choose 2 CNR model in our study. And first one is Lincoln-Petersen model. Second one is CIS model. Lincoln-Petersen model is the simplest model in CNR method. I will show it with graph. To begin with, one would capture a few animals, and the market animal ratio should equal to the number of bird capture C over the total population N. To close the deal, one would capture again, and in this second capture, we will see one market animal. This means that this animal is both captured in the first capture and second capture, and the market animal ratio should equal to the number of market animal N over the number of second capture R. Lincoln-Petersen has 2 assumptions. The first one is the population N in between 2 captures does not change. The second one is the probability of the animal being captured is independent and identical over time. This will go 2 problems. The first problem is that the server population is likely to change between clouding events. It is not likely to maintain in the same number. And the second one is the chance of discovering a server is not IID because the server allocation is biased to its approximate to the client. The next part is dataset. As far as we know, there's no public Twitch dataset available, so we borrow the API from Twitch and use the Node.js to implement it to the cloud platform across 6 regions. The reason why we deploy it so wide area is because the server allocation is depend on the location of client region. So such geo-diverse deployment can help us to validate the estimation method as many regions clusters as possible. And about the spatial analysis, we find that there are many IP address overlap. For example, the North Europe and the West Europe IP address is 99% overlap, and for the Central Australia and Korea, with the Europe, there are 90% of server IP overlap. So we divide the server cluster into the 3 regions, the Southeast Asia, West Europe, and the West Europe. We can notice that West Europe is larger than the other 2 clusters. And then we talk about temporal analysis. The servers are observed by repeat requests to the stream watched by 80% of viewers. So in general, if there are more streams, the more servers we may observe. The black line is show the average hourly server count, and the blue shadow is show the value range of adding or -1 standard deviation. So we can see the both figure. There are peak in the noon and low in the night. It really makes sense that there are more viewers in the noon than in the night. And about the daily server count, we can see that the West Europe is much higher than the West US, and the highlight in red is mean that in the weekend, and in West US cluster there are no obvious difference between weekday and weekend, and about the West Europe cluster they are visibly higher in the weekend. Next, Wei Xiang will show how the CNR method applied to estimate the daily server count.
Hi, I'm Wei Xiang Wang, and I'm going to introduce the evaluation part. First is the experiment setup. You can see the baseline, which means the number of servers observed in a whole day. because the length of time is 24 hours. The traffic overhead for baseline is also very high. As for LP and CJS, both of them are CMR models. For LP, we need to sample twice in a day, and we sample at 8 a.m. and 4 p.m. respectively. As for CJS, it considers the samples in the past and in the future, so it only sample once in a day, and we sample at 4 p.m. Because of the number of samples, CJS traffic overhead is also 50% less than LP. This figure shows the estimation result from CJS and LP. You can see that CJS is relatively stable and it also fits the baseline very well. So we are going to focus on the discussion about CJS. CJS models use multiple captures to estimate server population. We figured that there are two parameters influence probing overhead and accuracy. One is capital D, which is the duration of each capture, and the other is capital S, which means the time spacing between the captures. This figure shows how sampling duration influences the estimation result. If the sampling duration is longer, it leads to low error rate but high traffic overhead. This figure shows how intersample spacing influences the estimation result. If the intersample spacing is longer, it leads to high error rate but low traffic overhead. So we need to adjust these two parameters in a proper way in order to find out the models with high accuracy and low traffic overhead. Our next step is to find out the best parameter combinations to make error rate lower than 10% and traffic overhead as low as possible. According to our experiment results, when S equals to 24 and D equals to 1, it has the best estimation result for the West US dataset. For the West EU dataset, S equals to 4 and D equals to 1. You may wonder why the value of S in the EU dataset is smaller than the one in the US dataset. It's because the variance of the data in the EU dataset is larger than the one in the US dataset. It needs more samples in a day in order to fit the baseline well. This figure shows the two estimation results from the models with best parameter combinations in the two datasets. Actually, they both fit the baseline very well, and their error rate are roughly 7 to 8%. We are going to see the conclusions. First, both LP and CJS effectively reduce the probing overhead for server number estimations. Second, CJS is ideal maintaining a low estimation error when the traffic overhead needs to be low. Third, different parameter combinations for dataset in different regions are needed to maintain high accuracy and low traffic overhead. The last one is CJS model also performs well in new 2021 US dataset. These are our conclusions. Thank you very much. We are also interested in the robustness of CJS. There are some possible reasons may lead to probing failures, such as product failures, network congestion, and server maintenance. Actually, CJS is quite robust because it estimates from samples both in the past and in the future. Its estimation might be off during an outage, but will update soon as the system recovers. This figure shows the estimation results with some sample loss starting from November 2nd, and as you see, CJS still remains stable after the system recovers. So CJS is very robust. We also apply our CJS model on new US dataset in 2021. CJS can still fit the baseline very well even if the size of the cluster grows into 500 servers.